A line is a one-dimensional figure because there's only one direction of focus. A square is a two-dimensional figure because there are two directions of focus, the length and the breadth. A cube is a three-dimensional figure because there are three directions of focus, the length, the breadth, and the height. If you are to meet someone at a location, you give that person the longitude, the latitude, and the altitude. And that is what we call the spatial coordinate. But there is something missing. What should this friend of yours who you are about to meet do with these coordinates? There's one important information you haven't told this friend of yours. Yes, time. It's also a directional figure that makes up the four-dimensional space of our universe. Examples of these four-dimensional figures are hypercubes, hyperspheres, and Klein bottles. A dimension is the size or distance of an object in space in one direction. Someone might question how time fits into all this. That's if length is measured in meters and time is measured in seconds. They don't correlate, right? The journey to the joining of space and time started when there emerged inconsistencies between Newton's laws of motion and the laws of electromagnetism. That was the speed of light. Now, Maxwell theorized that the changing magnetic field giving rise to the changing electric field formed the electromagnetic force. And this was self-propagating, which was predicted to be moving 3 times 10 to the 8 meters per second. So Newton's theory question: what happens when a person is measuring the speed of light and moving at the same time? Will the speed be greater than the predicted speed of light? Later, scientists Michelson and Morley performed an experiment to measure the speed of light, and that's to certify whether the rotation of the earth affected the speed of light. Because since the earth was moving, if you shone light on the earth, the speed of the light should change. But they observed the rotation of the earth did not affect the speed of light. Albert Einstein then came into the picture and then introduced his theory of relativity, which made the speed of light constant in all inertial frames of reference. He corrected the notion of the speed increasing for a moving person by explaining that observers would experience space and time differently when moving at different speeds relative to each other. And this was what birthed relativity. Space will contract and time will dilate when moving at relativistic speeds. There are speeds approaching the speed of light, but the speed of light itself will remain constant. Minkowski, who was the teacher for Albert Einstein, theorized later that relativity is more geometrical than theoretical. It was a geometrical relationship between space and time, that's the time dilation and length contraction. This arose from the way space and time behave when objects moved at relativistic speeds. And this was where the space-time was coined into one thing. Diagrammatically, this seemed impossible when pictorially fitting the 3 spatial coordinates and time on a graph. This was because the time, as we said earlier, was having different units than the spatial coordinates. But Minkowski proposed that we should measure time as a length when it is multiplied by the speed of light, ct. If the speed of light is 300 million meters per second, then 1 meter is 1 over 300 million second. And we label it as CT on the graph. An object in a stationary position will not be moving in any of the directions on the spatial coordinates, but it will be moving forward in time. This line the object makes becomes known as the world line. A moving particle would be a diagonal line in the direction of the coordinate it was moving and also the direction of time. If an object was accelerating, it will be moving in curls. If a representation of light which moves in all directions is drawn on this graph, it will depict a light cone as named by Minkowski. If a person who was standing still observed the light on the graph, his world line would intercept the light cone, and this we can call an event. So the light cone origin could be event A, and the meeting point of the world line and the light cone could be event B. Just an illustration. Now on this graph, since we have incorporated time just as we could have negative coordinates for space, we can have negative coordinates for time, which will signify the past. So on this Minkowski graph, we can have the past and the future diagrammatically represented. So if a stationary observer is at a point on the light cone, let's say A, then all the light that came from beneath to converge at a point A is the past of the stationary observer. So we want to find Schrödinger's cat. This time we know it's not in a box, or maybe it's missing somewhere in space. How can we find Schrödinger's cat? This is where we apply geodesics. In space, a metric is what is used to measure length and angles using a grid placed tangent onto an object. To calculate the distance on an object, we sum the distances on the metrics leading to the endpoint. A geodesic is a straight line on a curved surface. Examples of geodesics is longitude and the equator. Those are great lines that circumvent a huge spherical body. Curvature tensor is an object that compares how geodesics evolve. When the surface is curvier, the geodesics converge or diverge, but when the surface is flatter, the geodesics are parallel. Without an external force, objects move through geodesics in space and time. The Minkowski metric is the space-time in empty space where no gravity exists. Everything moves in straight lines on flat surfaces. But when there is gravity, this is known as the Schwarzschild metric. Therefore, to find an object in space, we know which metric to use and how to find them. Now, dealing with relativity and then geodesics, we can say that the curvature of space-time, as we explained in gravity, is what causes gravity as we know it. The movement of heavy objects through straight lines gives us gravity. So with this, when we know the three spatial coordinates and time, we can be able to use metrics. Any of the metrics, Schwarzschild or Minkowski, to be able to find this Schrödinger's cat. So this is what we have for you folks. This is Einstein in a Flash. Until next time, bye bye.